right, honey, what's your name? You got that sugar, can I get a taste? I hope nobody stakes a claim, 'cause I've been gifted what I'd pay for. I don't know where you're going, and I don't know if you'll stay, but I bet I could change your mind if you just walk my way. I could be your Fuji apple, baby, lend a kiss, don't leave me hanging, 'cause I think I'm falling. I could be your one and only if you promise just to hold me, 'cause I could lay like this just for a while. Expensive words on red wine lips. Wanna know the flavor, could I get a kiss? I like your rhythm and I like your rhyme, so sing a little louder, 'cause I'm jiving, I don't know where you're going, and I don't know if I care, 'cause anywhere you need to be, baby, I could take you there. I could be your Fuji apple, baby, lend a kiss, don't leave me hanging and call me crazy, but I think I'm falling. I could sing you any song you want, be a nightlight when your day gets dark. I'm following my heart that I am dropped and left for way too far. The pink never leaves my cheeks when you're around, and the leaves are turning green, so you better come pick me now. Come on and pick me now. I could be your Fuji apple, babe, might love you till I drive you crazy, but I only mean the best, so take my hand, I'll take care of the rest. I could be your Fuji apple, baby, lend a kiss, don't leave me hanging, 'cause I think I'm falling. I could be your one and only if you promise just to hold me, so I hope you'll catch me, 'cause I've started falling.
All right, welcome back, everybody. That was the song Fuji Apple by someone who may or may not be a peer of yours in COMP110. I don't think by FERPA rules I'm allowed to say whether or not someone is actually in this class, but if you enjoyed that song, I would encourage you to follow on Spotify, check out the Instagram account, and like and subscribe on YouTube. Love seeing the songs of students at UNC. So if there are others of you who are musically inclined and would like to have your music open up class, let me know, and I'd love to highlight it. I just realized that I updated the animation on this slide and it looks like the ship is sinking. That's a bad omen, so we're going to continue on. Today we're looking at references, and this is something we introduced last week, and something that sounds kind of scary, and in some cases is mutations and what that means. But to just give a quick overview of today's goals, we're going to start with global variables. Great work on the most recent project where you were introducing or working with global variables for the very first time in an intentional way, and using that to keep track of your players' points. We'll be moving through the games that you all developed, and by the early looks of things that have come in, a lot of funny creativity in games that we're excited to play. We're going to look a little bit more closely at reference types, and list is an example of a reference type. And we know that it's a reference type because when we are diagramming these, we're drawing arrows from the name that we've bound on a frame on the stack to the actual list in the heap. And that has some interesting implications that we need to be careful about. And once you understand them, you can avoid all sorts of confusing, surprising errors. But one of the reasons why we have diagrams in our repertoire is to make references easier to understand. So today we'll sort of get to the bottom of that. And lastly, I'm hoping to give you a very brief introduction to what a sorting algorithm is. And this relates to the idea of references. And then we'll talk about how in this class we can sort data as we need without having to implement algorithms on our own. This is a well-solved problem, and Python has some built-in functionality. Before we get there, a few quick announcements. There's a new exercise out, more functions that you can explore. There's 3 different Python files and 4 functions in total that you'll be writing. These are going to be focused on working with while loops and iterating through string data as well as list data. So you're going to get some practice with some of the concepts that we've been looking at over the last week. And this is due on Monday, March the 8th. We've got a quiz coming up a week from today. This is before the next set of wellness days, so we'll be all wrapped up for those, which are the following Thursday, Friday. And that's actually, this date is wrong. It's not March 4th. It is March 9th. So let me fix that. That's scary. The Tuesday or Thursday is March 4th. This is March 9th. So a week from today is when the next quiz will be. And it's going to be focused on lists, loops, and some of the reference types that we're looking at today. Right? So I want to go ahead and jump into a warm-up question. And this one is going to involve some of what you looked at in the most recent project with global variables. And we're going to look at what are the implications in an environment diagram. Without diagramming this particular code listing, what I'd like you to try doing is tracing through it, using your best reasoning and approximation, and approximate what you think the printed output will be. I'm going to open up the poll. Actually, it's already open and some of you are responding. So do respond to that. And once there are, a good number of you who have been able to take a minute to think through this, we'll talk through it together and try diagramming it. All right. It looks like about 3/4 of you have been able to respond. And of those of you who have responded, 60% correctness. So there's some kind of tricky things going on here with this global variable X and various ways that we can refer to a name and some of the rules that apply to name resolution when we do various things. So before I reveal the answer here, let's actually jump into this code listing. And I want to walk through this with a diagram because I think once we diagram this, some things will make a little bit more sense. One thing I'll mention is that there will be a lesson to upload on Gradescope. It'll just be the last diagram we do together, and that will be live closer to when we actually do that diagram. But these first few exercises that we're moving through together are just follow along. You're not going to submit these on Gradescope. Okay. So we've got just a code listing here, and as you kind of traced through this and worked through it on your own and in your head, so to speak, you notice that there's this variable X that must be a global variable. There are a few functions, and then we're referencing X in those functions, and we're printing X from outside of it. And so this is scenarios like this where you have to be very careful with name resolution and understanding the way local variables are different from global variables in a language like Python. So I'm going to set up a stack, and on my call stack, we're going to have our globals frame, right? And this globals frame is going to have X defined in it, which is initially 0. And then we've got these 3 function definitions, F, G, and H. So F, G, and H. And each of these is going to, as you know, refer to a function. And I'm just going to try and move through this very quickly because there's nothing really new and exciting here. So this is the function on lines 5 through 6. G is the function on lines 9 through 10. And H is the function on lines 13 through 15. All right. So we've got our globals frame. And the first function call that we evaluate is this function called f. Now, We move through our rules. Do we know of something named f? Yes, the name f is bound to the function defined on lines 5 through 6. Okay, so this is the function definition we're talking about. We see that there are no arguments. That corresponds just fine to a function that has no parameters defined. So this looks like a valid function call. And if we wanted to look ahead, we could see that this is a function that returns none. All right, so let's go ahead and set up our frame, f. And our return address is line 18. And there's no parameters to set up, so we're ready to jump in with just this. So we jump in, and this line is pretty tricky, all right? What is this line saying? Well, whenever you reach a variable assignment, or in this case, it's actually an initialization line, but I did something a little bit tricky here. I didn't declare this as x int is assigned 1, right? However, because this assignment statement is happening in the context of f, right? And we didn't declare x as global, what Python interprets this as is, hey, you're actually declaring a variable named x, and its type is implicitly going to be an integer, right? This is one of the reasons why we encourage you to not rely on implicit typing, because when you write a line like this, it's very easy to assume we're referring to the global x, when really what we're doing is sort of this nonsensical thing of setting up x with a value of 1 in our local frame, right? And the reason for that is because unless we declare inside of a function definition, like we'll see that we do down here on line 14 and the age function, unless we do that, whenever we assign to a variable within the context of a function body, what we're saying is we want to be working with a local variable. And remember, this is the same as, x int is assigned 1, but we prefer this because it makes it much more explicit and concrete that we're declaring a variable there. And there's one more reason for that, what I'll come back to, right? So when we return from this, this is a function that returns none, so the return value is going to be none. And this is a procedure, like you all wrote in the most recent project. And when you have a function that returns none, when you get to sort of the last line, there doesn't need to be a return statement. We're going to go back to the return address, which was line 18. So when we print x the first time, we are no longer in the frame of f, right? And let me actually write this return value a little bit lower so it's more obvious and clear that this function has returned, right? So the f function is done. So the frame that we're looking at as our active frame is the globals frame, and x in globals is still bound to 0. We didn't change anything about it. This call to the f function, all it did was set up a new variable x with a value of 1 and really did nothing with it. All right. So what about this next function call to g of x? So once again, we ask, we're in globals. Do we know what g is? Yes, g is the function declared on lines 9 through 10. So it's this function. It has one parameter, x is an integer. We're giving it whatever x's value is. X in globals is declared as the integer, so it's going to be given the value of 0. So that's fine. And it looks like a valid function call. So let's set up our frame for g. So g return address is line 20. And the parameter x, right? So we're saying, okay, well, let's figure out this called g of x. X in globals is 0. So this is the same as saying g of 0. So we're passing 0 to this x parameter. All right, so x is 0 here. Now, we jump into this function definition and we say, okay, x is assigned 2. Well, what is our current frame? Our current frame is the lowest frame that has yet to return. So that's this one. So we're currently in G. And so when we refer to x, we're actually referring to this parameter x. Notice there's no association other than sharing the same name. This is kind of a coincidence between these two x's. So x is now going to be 2 in this frame of the call to G, right? And we reach the end of this call to G. There's no return statement here, but that's okay because this is a function that returns none. It's a procedure. So our return value is none. And this first print x printed 0. And when we return back to G of x, the second print x, well, what is our active frame? This frame is returned, this frame is returned. So we're back in globals, right? We're back looking at, well, what are the names that are bound in the globals frame? And x is still 0. So it's a double sort of tricky example here where even though it looks like we assigned x these two different values, it turns out we did, but we did so within the context of those function definitions. It's not until we reach h where we see, oh, we're actually going to influence this global variable. All right, so let's continue on, and then I'll take a look at the questions. So this call to h is no parameters in the definition, no arguments in the function call. Looks like a valid function call, so let's go ahead and set it up. So h, return address is line 22. And we jump into this function. Now, here's where things are different. We encounter this global statement. So what do? Well, here's where we don't have a formal convention for signifying that x needs to be, done anything special here. If you would like to, you're free to say, global x or something like that. It's just a note to yourself. But technically, there's going to be nothing that's actually here. We're just saying, okay, if you would assign to x within the context of this function definition, we're not talking about the local x, and local meaning within the context of our frame. What we're saying is you're actually going to influence the global x, or the one outside of the frame. So when we assign x to 3 here, or 3 to x here, that's actually going to influence the global variable x, right? And the key distinction, and this is why we wanted to sort of get some practice with this in your latest project, is what we're declaring, this global keyword is saying, hey, for this variable, and if you had multiple variables, you would just make a list of them if you were referring to globals. Hey, we're referring not to x inside of the frame. Whenever you refer to x from here on, it's going to be the global variable x, right? So we changed x to 3, and then we reached our return. There's nothing left to do here at the end of this procedure, so the return value is none. And when we go back to line 22, this is where we would print 3, right? So the first print value is 0, second print value is 0, so this would be our output. 0, 0, 3, which 60% of you identified correctly, so great work there. Let me take a look at the questions that have come up. Okay. So one question, that's a great question. If we had put a return statement in function g, so in this function here, would it still have printed 0, or would it have printed 2? I love this question. This is a fantastic observation. And I want to play this out just a little bit. Okay, so let's imagine here that the return type was integer. And that means we could return x. So when we return x, this expression evaluates to 2. However, we're not doing anything with this expression. So let me actually simplify this just a little bit for the purposes of this question and moving through it, and say, okay, let's imagine that all we did was call g of x and then we print x. Well, if we had done this, and I could try running this. So Python run lessons ls14. So we'll see this doesn't have any impact. X is still going to print out, as 0. There's no impact of returning x from g. However, if we had said here, x is assigned the result of g of x, the x we would be referring to here would be the one that's in our globals. And so in this case, if we were to evaluate this code, I need to save it. If we were to evaluate this program, we would see that it does have an impact. The only way a variable's value is going to change when we have a variable like a number is if you assign something to it. And that's what's going to cause the contents of its location in memory to be updated and changed. So the fact that this returned wasn't very important, right? It was, what did we do with that return value? So when this expression evaluated, if we did nothing with it, x's value in globals wouldn't change, but if we assigned to x with that value, we would have updated x's value. And that's how we could have made that work based on the question. So let me return this back to where we were and take a look at the other questions. Okay. All right. So the question is, when we assigned x to 2 in G, is this still a local variable? So one of the reasons why we set up our parameters in the way that we do, so remember in this function call to G, we're saying, okay, evaluate x, that's our argument, and that x's value is 0 at the time, and then call G with x of 0. And when we did that, we set up the x such that this was, initially 0. And then when we reassigned it, we said, okay, well now x is 2. Parameters are, for all intents and purposes, local variables, just the same as other variables declared within the context of a function definition. The key distinction is that parameters are automatically initialized on your behalf, right? This x is initialized as part of this function call. Whereas a local variable like the one we defined up here, it's initialized inside of the function call. And so that's the only real distinction between these two concepts. What if the x's had different names? Good question. So let me just play this out real quick, and then we might move on to the next example after this. So if this were y is assigned 1, and especially if this were y is an integer assigned 1, then the only difference in our diagram would have been we were defining a variable named, say, y. Similarly, if this were y and y were assigned 2, this would actually been the same example as what we had above almost effectively, but we would be using a parameter to get the name of y in. So notice that we don't want to redeclare a variable y. That's sort of that would be bad practice to have a parameter whose name is y and then use a variable named y. But what this would have had the effect of is very similarly, we would have had a parameter y, and x, which the value at the time was 0, would have been assigned to y, and that would have caused us to set up a parameter y. So what we name our variables inside doesn't matter. However, in this example, in H, if we had said, global y and y is 3, we would have been establishing a global variable named y and giving it a value of 3. Now, this is a particularly dangerous thing to do, and this would be considered bad practice because we didn't ever declare a global variable. So technically, you would really want to declare a global variable before accessing it in this way, but I don't believe Python would prevent you from doing so. There's one opportunity here to mention, so let me actually return the example back to where we started. All right. One thing that's actually very handy about the way we declare our variables is if we had said global x in this way, and then we tried to redeclare x as an integer that's assigned 3, and I tried to run this program one more time, and I got to save it. After saving it, if I tried to run this program one more time, you'll notice that we get an error saying, this annotated type, which means we're trying to declare it, can't also be global. You can't redeclare the name x to mean something else. After we've declared, we're actually referring to the global variable. So there are some reasons why, if you get in the habit of using these type annotations in modern Python, it can really look over your back and help you avoid unintentional errors. Can a parameter be a global variable? Great question, and I don't think there's ever a case where you would want to do that. So I'm going to go out on a limb and say I don't believe that's possible because I don't believe there's a use case I can imagine. Yeah, I'm pretty sure that's just a syntax error. So not really. Typically you use one or the other. And as you become more capable as a programmer, you tend to prefer parameters over global variables for some of the reasons you may have started to get a feel for in your project. Because if one function modifies a global variable and you're trying to track, well, who actually changed this global variable, it's really hard to track down and to reason about. It's much easier to reason about functions where you see exactly what their inputs are and then their return values than those who modify global variables. Why did we define x in function f? So this is that's a great question. This is really a silly example. And there's no good reason for doing this. Like, this is a function you would hopefully never write. However, the same phenomenon can and will exist in real world examples. So for example, if you were to try and go and take and look at your project, and the functions that you wrote that involved, this global keyword, if you removed the global keyword, your program wouldn't work the way you expect it to. That global keyword was important for being able to modify the points variable that was global. So if you took that out, you would see that like whatever updates to points you had inside of your functions in the most recent project wouldn't have had any impact on the global variable. And so this is really trying to give an example of why it's dangerous and why you have to be very careful when you're using globals, because you might think that, like I think about 20-30% of you thought that X was going to have an impact on the global X, or this assignment statement would, and it turns out it didn't. What if we did print g of x here and we returned x? So yes, that's a great question. This is going back to a question that was asked earlier. So imagine we did return x from g and we printed the result. Well, in this case, we would have printed x is 0 because f didn't change 0. In this case, we would have, x would have been 2 when it returned, so 2 would have printed. But then when we printed what is x in the globals, effectively, it still would have been 0. So this wouldn't have changed anything about the x that's globals. It just would have printed 2 because that's the result of this function call. Good question. All right, when x is 2 and g of x, the x is a local variable like it was in f. So when x is 2 and g of f. So yes, and it's a local variable for the reasons we mentioned a little bit earlier. So the question is this a local variable? Yes, and it's a local variable by virtue of already being a parameter. If our parameter name was y here, this would have established a new local variable named x, just like we saw in the f function. All right, so the only way that you're going to influence a global variable from within a function by reassigning its value is by declaring and saying, hey, I'm actually, in the context of this function, whenever I use the name x, I'm actually referring to the global variable x, not something that's going to be defined inside of this. Great questions here. We've got one more challenge question that I want to turn your attention to. And this is, and I'll open up the poll for this in just a moment. And actually, there's not going to be an asynchronous. That asynchronous link is going to be the same as what you saw before. So let me just say that if you're async, no worries on responding to this, but do think through it and imagine what you would respond. So there's one piece of there's one line in this code listing that we need to talk about, and that's line 8. So for some quick context, if we just look at what's going on in this code listing, we see that there's this function named sum things up, and it has a parameter that's a list of integers. All right, so x's is a list of integers, and this is a sum algorithm, hopefully, and we've got a while loop, so we're moving through in a funny way are the items of our list, x's. And one of the things we've talked about pop, and we've talked about pop where if you call this method on a list, list name dot pop and then parentheses, it's going to remove the very last item of your list. So this will get rid of the last item of your list. What we didn't talk about is it actually does return it to you. So if you wanted to use that value, and we're going to use that value here, then we could. So this has the effect of saying, okay, take the last value of the list and evaluate to that and remove it from x's, right? So in other words, when we call, imagine a list like, 1, when we call, and let's say this is x's.pop is an expression that will ultimately evaluate to 1, and it will have the effect of x's now being an empty list because we're removing that last element from the list. Right? The same is true when you use, we talked about also you can call pop and give it an index and say, hey, there's a specific element, an item in the list at this index that I want you to pop. It will also return or evaluate to that particular value. So what I'd like you to do is think through this code listing. Again, you don't have to do a full diagram on this. We'll diagram this one together in just a moment, but imagine what happens in this code as you trace through it and respond with what you think is the outcome here. All right. Looks like most of you have had a chance to think through this, at least on a first pass. And this is one of my favorite questions in COMP110 because at this point in the semester, it feels like we've got a good handle on all of these concepts and there's nothing too tricky happening here. But this one's a shocker. And only 30% of you actually correctly reasoned through this because it involves some implications that we haven't really discussed head on yet. Most of you, 45% of you, responded 6-6. This is a very logical response. This is in many ways what you would expect to be the correct answer. Unfortunately, it's not correct. Right? And we'll talk about why in just a moment. Another quarter of you responded in infinite loop. Turns out there's no infinite loop here. This program will complete no problem. The correct answer for if you were to run this program and see what happens is that you would see 6 printed from this first print statement and 0 printed from the second. Based on everything you know up until this point, this is a pretty surprising result. So let's try and get to the bottom of why that is and make sure our mental model for lists and reference types is sound. So I'm going to jump back over to this example in VS Code, make this a little bit bigger, and let's talk through this. All right, so this is one that I would encourage you diagramming along with me, and then we'll take questions as soon as we're done. All right, so in globals, so we've got our stack, and globals is going to have this function sum things up. And I tried to make a terrible pun here to give you a hint that something strange was going to happen in this relative to what we've learned so far. But once you're comfortable with this, there's nothing really that strange about it at all. And it's a very reasonable why this behaves the way that it does. All right, so this is a function from lines 4 to 10. And then we have on line 13, a list. We see that we have a list literal here. So we know that this is going to be a list of integers. And we have 3 elements. So there's going to be 3 indices, 0, 1, 2. And those values are 1, 2, and 3 at each of those indices. All right, so let me set up my list on the heap, and I should label the heap here. All right, so there's my table for the items of this list. This is the heap space. And this list is being bound to nums. So one of the things we mentioned last week is that whenever you're using what we're now going to call a reference type, and list is an example of a reference type, we have an arrow that goes from the name on the stack to the value that it's referencing on the heap. So we're saying nums is a reference to this list. And I'm actually going to draw this arrow in a special color because this is really where the emphasis of this example is. It's the fact that nums is this reference. And so whenever we refer nums, we know that, okay, we can then go look up what is in this table or in this list. Okay, so now we call this function. We reach a print statement, but first we need to figure out, well, what is the result of calling sum things up? So first we ask, is this a valid function call? Well, we've seen the definition for sum things up, so yes. And then we look at our argument. Its type is a list of integers. That corresponds to the single parameter, so it looks like this is a valid function call. So we're ready to set up this function call frame. So the frame's name is sum things up. And the return address is line 14. And we have x's. And what is x is going to be? Well, this is where we need to be careful. This is what we mentioned in the previous set of videos. X's is going to be a reference to that same list. And remember, where this arrow points is irrelevant. Both of these arrows just refer to this list. So this is no different from me drawing an arrow that went, up and above and said, okay, we're referring to this list. So now X's refers to this list. We didn't copy this list. We didn't make a new list. We've only got one list whose values are 1, 2, 3 in memory in the heap. Okay, great. So we've established our parameters. We've established our frame. We're ready to jump into this function call. Right? And on line 5, we see that there's a variable declaration. We're declaring a total variable. And this works a lot like what we saw before. Total is 0. okay? And then we reach a while loop. While the length of x's, so x's refers to this list, and its length is 3. While 3 is greater than 0, that's true. So we go into the definition or the while body here. And we're saying, okay, increase total by whatever this amount is, right? We're using that relative reassignment operator. So we have to figure out, well, what is x's.pop and what implication does this have? Well, remember, pop is going to remove the last item on the list. So that's 3. We're going to remove that item, and x's.pop is going to evaluate to 3, right? So I'm going to indicate this. For my purposes, I'm just going to scratch out that entry. So now this list doesn't have an element at index 2. It doesn't have the value 3 in it. But this method call just evaluates to 3. Whenever you pop a value, it returns the value that you removed from it, right? And we're taking that 3 and we're increasing total by that amount. So total is going to be, 0 plus 3, which is 3. Okay, we reach the bottom of our while loop. We go back up, and now we're going to test again. Length of x's. Well, now the length of x's is just 2, right? We removed one element from it. So while 2 is greater than 0, that's still true. So what do? Well, we go in and we pop again. So we pop, and 2 is the value of the item being popped. So this expression will evaluate to 2, and we've removed that item from our list. We've effectively gotten rid of it. And now we're saying, okay, total is going to be total's current value, which is 3 plus 2, which is 5. So now total is going to be 5. Or if I wanted to keep track of the ways that it was updated, I could say, 3 is crossed out to be 5. So we've updated total to include 2. We've reached the end of this loop. So we go back up, and now we're asking, well, what's the length of x's now? The length of x's now is 1. 1 greater than 0, that's true. So we go in, and once again, we pop. Well, we're going to remove the last item of our list. That's 1. So I'm going to remove that item. So this is 1. And now we're saying 1 plus total. So 5 plus 1 is 6. So total is now going to be 6, right? We go back up to the top of this loop, and we ask, well, the length of x's. Well, now there's nothing left in this list. So its length is 0. 0 greater than 0 is false. So this loop is completed. And we return total. So the return value is whatever total is. Well, total was 6. Okay, so we return 6 to line 14. Right? So now when we print, this first print statement would evaluate to 6, right? Here's the interesting thing. If we think about, well, we're back in globals, this nums variable, right? This nums variable that we set up that referred to the list that was initially 1, 2, 3, now it's the list that actually has nothing in it because we modified it and we changed that list from within some things up. And this is one of the key differences between a value type, such as integers and booleans and floats, and a reference type, where when you call a function and you give it a reference to the same list, if you change something about that list, you've changed it back where the function call originated from. So nums in globals now refers to this list that's empty. So let me move through the second function call, and then I'll take questions on this. Right? So the second function call is very similar. So we are calling some things up. We know it's valid because it's the same function call as we made before, but this time around it's on line 15. And x's is once again going to refer to, so x is this parameter, is going to be assigned the same thing as nums in globals. So nums in globals is a reference to this list that's now empty. And so x's is now going to be a reference to that same list that's now empty, right? And you can probably already figure out, well, this is what's causing this sort of bizarre and unexpected output. We changed something about this list in the previous function call. So now when we go and use this list later, it doesn't have the elements in it that we thought it did initially, or that it didn't initially. Okay, so we jump into this function call. We set up total. Total is 0. And now we ask, well, length of x's. Length of x's is 0. So 0 greater than 0, that's false, right? And so we don't loop at all. There's nothing to pop, right? This is just an empty list. So what do? Well, we return the total. Well, total in the current frame that we're working in is 0. So the return value here is 0. And that's what would cause 0 to print out from the second print statement, but 6 to print out from the first print statement. This is one of the reasons why references and diagrams are a very valuable tool in understanding what's going on behind the scenes. Before we used diagrams in COMP110, this was one of the most confusing and sort of opaque, hard to understand concepts. Once you're comfortable with this idea of, okay, well, all my lists live in the heap. So whenever I refer to a list, like say nums, and pass that to a parameter like x's, what I'm assigning to those parameter values are references to that same list. So through the course of this program, x's referred to the same single list in memory that we set up in globals. And this is a key difference between what we call our reference types, like a list, and what we saw like in the previous example where we have integers that aren't reference types. They get copied into the other frames and aren't references. All right, so let me take a look at some questions here. Thanks for the compliments on the pun. Is there a way to remove an item from a list without doing so permanently? That's a great question. And the way I'll answer that is yes and no. You could store the thing that you removed in a variable or in another list. And if you did so, you could then put it back when you were done. But there's not like a temporary pop here. Typically, if you're trying to be careful about not modifying the same array or list, what you would do is you would set up a whole new list in here and copy elements that you want to it. The previous implementation of sum, we didn't change anything about the list, right? And that's actually a good practice to try and implement and to adhere to. If you write a function that changes something, about a reference that it's given, you typically want to make that very clear in the doc string and say this function will modify the contents of the list that you give it, because it is hard to reason about functions that change the contents of some list that you give it and you don't really know how or why. We'll see there are some good uses for this in just a moment. If we had total greater than or equal to x's.pop, would it be an infinite loop? There are definitely ways that you could make this an infinite loop. It would be a little bit weird to condition this on total. If we didn't pop here and we used length as our conditional, but we used like a variable like I, and we didn't change the length, then this would be an infinite loop, right? Typically, you don't really want to write loops like this. This is what I would call bad practice. In fact, I should probably say don't do this. You can do this, and there are some cases where you might want to, but you typically don't want to do this. Typically, you want to use a variable as your index and move through your indices. And it's rare that you would actually want to pop the values off it to process a loop. This is a pretty dangerous thing to do for the reasons that you see. It looks like it worked the first time, but then the second time you get a very different result. And that's surprising and hard to reason about. So lists act differently than integers, since here the global value changed, but with ints it didn't. This is a great question. And one of the reasons why I wanted to put these examples back to back is because there is a distinction here. And let me think about how to try and make this distinction a little bit clearer. There's two phenomenon going on here. And let me just actually change this example to where, what if instead of saying x's.pop here, what if I had said, this would be a weird thing to do, but what if we had said x's is actually, we're going to ignore that value that we were passed in. What if we assigned x's to be 1, right? A list with a single element in it. So notice here we're reassigning x's locally. Let me just give you a quick demonstration of what this would look like and try and move through this very quickly, because this will hopefully illuminate the difference between what we saw with the previous example and this one. So I'm going to abbreviate the name of this function to STU, stew. So we've got our sum things up, our stew function. and we've got in globals. So I'm not going to completely reproduce this, but in globals, we would have nums, nums is the list with 0, 1, 2, and 1, 2, 3. I'm not going to label this just to try and move through this very quickly. Actually, list event, right? And that's globals. And then we have this frame for sum things up, right? And x's was initially assigned a reference to that same list, right? And we had a return address and some other details. I'm moving very quickly here because I want to emphasize what happens on this line and the difference of things that we're talking about here, right? So x's is a local variable, right? It's local to the stu function. It just so happens to reference a value that's in the heap, right? So it references a value. So if we say pop or change something like x's index 1, if we change that, we would be changing that singular list object. But here we're doing something very different, right? We're reassigning x's. So what would this have the implication of doing? Well, before we worry about this, let's remember that whenever you see a list literal, that's setting up a brand new list object on our heap. And in this case, it's just a list with one item in it whose value is 1 at index 0. And when we assign to a list, just like what we saw down here, when we assigned nums this list, we set up this arrow. Well, in this case, we're saying x's is actually going to be referring to this list object that has one item in it. And if we were to move through this, we would pop 1. This would be an empty list, and we would return 1. But if we looked at, well, what is nums and what would happen the second time we called this? Notice we didn't change anything about that original list. So there is a key distinction between the difference between a local variable and a global variable. And the only way we can, fundamentally change, nums, you could imagine we could also say something like global nums here. And now we would have effectively a way of accessing that global variable nums directly. There is a distinction between those things. One of them gives you the ability to actually change what's in the box or assigned to a variable in the globals frame. And when we have references, like we're seeing in this example and with lists, what we're saying is two things can have arrows that point to the same object on the heap. There is nuance there, and it takes some time to let this concept sink in. We'll see some other examples of it. So I would encourage stopping by office hours as well, or tutoring tonight. And if you want to talk more about this, it's a great question to talk about. So the question of when we draw a diagram with x's.pop, do we leave it by scratching it off or leaving it drawn? Because it can get messy, algorithms that like pop things off and append them in diagrams, we tend to avoid those, especially on quizzes. So it's really up to you which one you would prefer. I tend to like crossing something out so that the next thing you append, you would just remember that you'd have to use the next index that was the next one after. So if you popped everything off and then appended something, you'd be back at index 0, 1, 2, and similarly. We tend to avoid these types of questions because they are tricky, but it's important to understand that this dynamic is very much at play. And until you understand, why this program resulted, and let me go back to where we started, in two very different results by calling the same function, it can be very confusing as a first-time programmer. The reason is we're able to reference the same objects on the heap. How do we draw an empty list on the heap? Great question. And I apologize for not having guidance here. We're not going to count off on the last exercise or the last lesson for this, but the way I would indicate it is just a list with nothing in it. And then the first time you append to it, you would just say 0 and 110, let's say, is what we appended to it. But an empty list, you're fine just leaving an empty header and nothing in it. Great question. Can we assume anything changed within the heap is changed permanently, changed when referenced to all other functions? I don't want to make a statement that's quite so general, and we'll see some other examples, but you can assume that if two places in your stack have arrows to the exact same object, or they both refer to the exact same object, then anything you change about that object, like a list, will be reflected in any of those references. And one of the ways I like to explain references is it's kind of like, Puff Daddy or P Diddy or Puffy, like 3 different names for the same person. But if none of those names are actually the person, they just all refer to the same person. How would this work if you had appended? So if you append, if our function had appended, we could see that we could get different results. But if you started adding items to this list or changing specific values within the list, then the list would grow or change. When you got back to globals, it would still reflect the same thing. The key idea here is you can have multiple names that are bound to the exact same object on the heap. The differences between references and values. Yeah, let me talk about the differences between references and values. When we have something like, x is assigned 5, and let me actually make this a more explicit declaration. X is an integer that's assigned 5. We think of item or types like integer and Boolean and floats typically as what we call value types. And when we have those value types, it turns out that, the way we illustrate that on the stack is we would say, x has a value of 5. And then if you said, y is also, or let me do this after, y is also an integer that's assigned x. Here we're going to say, okay, well, y is now 5 as well. So we're effectively making copies of this value, or it feels like we are. When it comes to reference types, if we had said, and I'm going to make this slightly different. X is a list of int, and y is a list of int. And we said, okay, x is the list 5, and y is x. Well, then what we would have on our stack is x would be a reference to a list of integers with the value 5 in it at index 0. And y, we're saying whatever x is, y should be assigned that same thing. Well, what x is really this reference, right? X is really this arrow. And this is sort of a funny thing to internalize and try and wrap your head around, but x is this arrow. X is not really this list. It's a reference to that list. And so what we're saying here is y is assigned a reference to that list just the same. Now it's very important, never, never, never to draw an arrow like this, right? Y is never, for our purposes in Python, going to be a reference to to x on the stack. In some cases, this can work out, but there are other ways where this very much will not work out. And the reason why is because this just isn't how it works under the hood. Under the hood, Python is keeping track of these arrows are sort of like what we would call addresses. They're locations in memory. And so x and y would both have that same reference to that same object somewhere else. We do not have a means in this language of saying, y is actually referring to x. No, what we're saying is x is a reference to this list, so y is also going to be a reference to this list. And that's at the heart of this distinction between values and references. All right. What I want to do next is give an example of where this can be useful. And there's not going to be another Polev question on this. Let me clear out my ink here. But there is an example that I think is going to be worth reasoning through. So we've got this function named swap, and actually, for the purposes of our today's lesson on Gradescope, this is the function that the diagram that I'd like you all to submit. So let's work through this one together. And before I work through this with you, I'd like to turn it over to you to try diagramming this on your own. Just as a quick setup, there's this function named swap. It's giving 3 parameters. And we set up once again an array or a list of integers, and we call swap twice, and then we print out those numbers. So we're ultimately going to print a list of numbers, and the question is what gets printed. So let me give you a few minutes here to work through diagramming this, and this will be the one that we wind up submitting on Gradescope. So take it away from here, and we'll come back in probably another 5 minutes. All right, it looks like we've got about half and half on whether folks have been able to get to the end of this or not. For time purposes, I think we'll go ahead and start talking through this and being sure that we can get through any questions on this particular example. And if there's time remaining at the end, we'll talk a little bit about what a sorting function looks like, but I think we're going to save that for some asynchronous content on Thursday, because that's an intense enough algorithm that it's worth giving it an appropriate amount of time. So we set up globals, and nothing too surprising up till line 10, hopefully. And we've set up swap. It's a function that lives in the heap. And its definition is up here. We can notice some things that are kind of interesting about it right off the bat. We've got x's is our list of integers. That's a reference type. And then we've got I and j that are integers that are value types. So you can have functions that mix and match lists and integers and any types of arguments that you expect to be given that correspond to your parameters. This is also a procedure. It doesn't return anything. So when you see a procedure that's given a list, that's something that should generally sort of put you on high alert. That probably means that this function is somehow going to modify the list that you're giving it a reference to, such that after this function call is done, that list's its contents have changed in some way. This is an idea that we actually call mutation. So I'm just going to make a note of this, because the keyword mutation is modifying an object, modifying something about an object. So in the previous example, when we popped from a list, that's a mutation. If you append to a list, that's a mutation. In this example, what we're going to see is we're going to change out some of the values of particular indices in this list, and those are going to be mutations as well. So anytime you reassign to an element in a list, or you pop or append, those are all examples of mutating, changing something about this object. Whenever there's mutation in a program, you need to be very careful about it, because like we saw in the previous examples, it can lead to surprising results. So let's think through what's happening here. We reach this function called a swap, and let's check our arguments to make sure they make sense. So nums type is a list of integers that corresponds to x's, which is a list of integers. That's great. We see the values 2 and 1, which are integer literals, and those correspond to I and j. So it seems like we've given the correct arguments, or the correct types of arguments. And this is a function that returns none, so the fact that we're not doing anything with the returned value is totally fine. So let's set up our frame for calling swap. The return address is line 11. And we need to set up our parameters. So our parameter names are x's, I, and j. Okay. What is nums? Well, this gets back to that idea of nums and globals really is this arrow. It's this reference to this list of integers. So if we're saying nums is being assigned to x's, the parameter, then x's is also going to be a reference to that list of integers. Now x's refers to the same list as nums, right? Similarly, we have 2, that's the argument that corresponds to I, and we have 1, that's the argument that corresponds to the parameter j, right? So we've established our parameters, and we are ready to jump into this function call. All right. The first thing that happens on line 5 is we're declaring a variable, temp. So if I set up this temp variable, and we are assigning to it the value of x's index I. So what is x's index I? Well, x's is this list here, and I is 2. So we look at, okay, index 2 currently has a value of 1 in it, right? So 1 is what x's I evaluates to, and 1 is going to be stored in our variable named temp, all right? So 1 is stored in temp. Or assigned to temp or bound to temp. All of those are valid ways of saying the same thing. Okay. I'll come back and explain the intuition and what's going on here in just a moment, but let's carry out the rest of this function definition. So next we need to take, well, what is the value of x's index j? This is the same as saying x's index and j is 1. So x's index 1. All right. Well, x's index 1, this is x's index 1 has the value 3 in it, right? So this is 3, and 3 is being assigned to x's index I. Now here's where we have to be careful, right? We're changing something about this list. We're changing one of its item values. So I'm actually going to replace it with a value in pink. So we're saying take 3 and store it at x's index I. Well, I is 2. So what we're saying is x's is this list, index 2, is going to be assigned 3, right? And on the next line, we're saying, okay, take what's in temp. Temp is 1, and assign that to x's index j. Well, j is 1. So x's index 1, that's this index here, that's going to be assigned 1, right? And if I were to actually cross out the values here, what I would have had initially was 2, 3. So we replaced 3 with 1, and then on the index 2, we replaced 1 with 3. All right. And then we reach the end of this function, and there's no return statement, but it's a function that returns none, so the return value of none is totally fine. Right. Now, when we get back to globals, that function call is done. If we were to print out, well, what is nums? So if we actually had at this point a print statement, print nums, what it would have printed out is 2, 1, 3, 4, right? And compare that with 2, 3, 1, 4. So the original list had 3 before 1 for its indices 1 and 2. The new list has 1 before 3. Or I shouldn't say the new list, I should say the same list, but it's been updated, it's been mutated, right? So what did we do? What did this function call actually do? Well, swap is the idea that if we were to write a docstring for this, what we would say is swap the values of the list at indices I and j. So what we're saying is on this line, it's saying this function should swap 3 and 1. And that's effectively what happened, right? 1 now comes before 3. We're swapping the positions of 2 items in our list based on these 2 indices. So there's this weird thing that's happening though. We're setting up this temp variable. If you tried to do this without a temporary variable, you would wind up overwriting one of your values. Like we would have had 3 and 3 in our list, and we would have lost 1. So we have to maintain, a third place to store in a value before we swap these values in our memory. It's like if we had, and I've used this example in class before, if you have cups that are filled with 2 different liquids and they would blow up if they touched one another, hypothetically, how would you swap the contents of those 2 cups? Well, you would hopefully have a third cup that you would pour one of them into and completely empty one cup, and then pour the other cup into the original, and then finally bring them back together, or replace that last cup with the original contents. Right, so what is this function call going to have the effect of doing? Well, in theory, what we hope it's going to do is swap these 2 elements, right? So swap index 0 with index 1, such that we have 1 before 2, and then 2, 3, 4, all right? So let's just trace through that, and then actually, let me check questions right now before we trace through that. Not seeing any quite yet, so let me go ahead and add this last frame, and then I'll come back to questions. All right, so we're going to call swap one more time. This time around, we're calling it on line 12. And we have our 3 parameters we need to set up, right? So x is I and j. All right. What is x's? Well, x's is whatever nums is in globals, and that's a reference to this particular list, right? So now we have x's in the second call to swap referring to the same list. We have the argument 1 being assigned to the parameter I, and the argument 0 being assigned to the parameter j. Okay, so we're ready to jump in. And now what do we do? We once again set up this temp variable. This is a local variable that's inside of the swap function. So temp has whatever x's of index I is. All right, so index I is 1. So x's of 1 is the value 1. Right? So x's of 1 is currently 1. That's what we're going to store in temp. Then what we're trying to resolve is what is x's of index j before we store that in index I. So x's of index j is the same as saying x's of index 0, right? Because this is our active frame. This is the one where we're looking up j as 0. So x is 0 is x's, and then in this table, 2 is stored in index 0. So this evaluates to 2. And we're saying take 2 and store it at x's index I, which is the same as saying x's index 1 is assigned 2, right? Because i's value is 1, x's index 1 is assigned 2. So x's index 1, I'm going to update this. It's no longer 1, it's now 2. All right. And finally, we're saying, okay, take the value in temp. Temp's value is 1, and assign that to x's index j. That's the same as saying x's index, and then we look up j is 0. X's index 0 is assigned 1. So we say, okay, x's index 0, that's currently the value 2. And now it's going to have the value 1 assigned to it, which was previously in temp. We reach the end of this function. There's no return statement, but because it's a procedure that returns none, the function call's job is done. It returns none. And when we get to this print statement and we print out nums, we're going to print out, the list literal representation of this, which would be 1, 2, 3, 4. So what we had the effect of doing here was using these indices. The point of this program was to show you that, hey, with a couple of swaps, we can actually move this 1, which is, if we were thinking about this in increasing order, it's kind of out of place, right? But if we swap it back 1, and then we swap it back one more time, and each time we do that, we would move 3 back 1 and then move 2 back 1. We effectively sorted this list by carrying out 2 swaps on the elements of it. Now, this isn't a sorting algorithm, but the same idea is going to apply. If we want to sort a list, we're going to need to swap items that are out of order with one another with some specific set of steps. Can you explain the index part of the index of blank? Yes. Let's look at this. Let me go back to line 6 here, because this is a place where we have multiple indexing examples, right? We've got x's of index I and x's of index j. When we are thinking about an assignment statement like this, we always want to figure out what is the right-hand side actually evaluate to. And actually, rather than doing it in here, because I've already changed values in this list, and I know it can be confusing to try and roll back in time and imagine where things were before, let's imagine something very similar down here at line 15. So imagine I'm just adding one line to our program. Everything else is the exact same up until now. If we said nums index 3 is assigned nums of index 0, right? So you'll hear me read this, and it's not a bad habit to get in the practice of reading this, nums of index 0, or index 0 of nums, I should probably say. So index 0 of the nums value is whatever's in this subscription notation, right? So the subscript 0 is referring to index 0. And remember, our index is, when we diagram this, it's what's in our left-hand column. Otherwise, it's just from 0 on up, right, for each item. So index 0 of nums means what is the value stored at index 0, right? And so when you go to look this up, you wind up having to follow. So here's nums and globals. We follow the arrow and we see index 0 has a value of 1 associated with it. So this would evaluate to 1. When we use indexing operators or the subscription operator as part of an expression, we go and we look up what's the value that's stored there. It's a little bit different when we think about, well, what's the impact of having subscription notation on the left-hand side of an assignment operator. So this line is simplifying to nums index 3 is assigned 1, or index 3 of nums is assigned 1, right? So nums index 3 is this particular entry, and if we evaluate this line, we're saying store 1 at that particular index. So this would update index 3 to have the value 1. Right? Previously it had the value 4. And so that's what, when you say the index of some list, the index is what's in the subscription notation, and the of part is the list that we're referring to. Great question. So there's a question of what happens when you output a list and when you print this output. So the output, when we print a list directly in Python, what's going to happen is it gives you the list literal notation. So this would be 1, 2, 3, and 4. And we can convince ourselves of this by actually going and running this particular program. All right, so let me hide this for just a second. And oops, I'll run this, and I'll note that we've just hit the end of lecture, but I will continue to move through these questions, and we won't get to sorting today. That's totally fine. So the output would be, it looks like a list literal. That's the default output in Python when you print a list. Why wouldn't temp be in the parameter? Why wouldn't we have a parameter for temp? That's a great question. And that gets to sort of the heart of this distinction between what are parameters and local variables, what's sort of the uses of these things, and why do you have one? Why would you choose one versus the other? In VS Code, notice that you can fold a function's definition, right? So if you highlight over it, there's this little chevron, and it points down when you have the function extended, and it points to the right when you have it folded. When you have it folded, all you see is the signature of this function. So notice the signature of this function is, you give me a list and 2 indices, and I will swap the values of those 2 indices for you in that list. The fact that we needed a local variable in order to do that isn't really something that we want the person using this function to have to think about, right? So when we define a function, we like to think of its signature as like, hey, here's how you use this function. Here are the buttons you can press, or here are the inputs you can give me, and here's what you can expect back from me. But for this function to do its job, it needed to know an extra little piece of information and keep track of some extra data. That's what this temporary variable is there for. And so oftentimes, this is sort of like just a behind the scenes when you're trying to carry out some operation, in this case swap, you'll need some local variables to keep track of things that you're working on, but that aren't really a concern to the person that's using swap. So down here, we really didn't want to think about the fact that this function needed an extra variable. And if we were to look at it as just sort of a quick preview, in a sorting function where we've got while loops, it's going to have local variables, 2 of them, to keep track of 2 different indices as part of its algorithm. And when you go to use sort, you really don't want to have to worry about those details. That's kind of the function definer's concern. So the difference between a parameter is something that you're saying, hey, in order for me to be a useful function, you should give me this information and I'm going to do something useful with it. And local variables are used for sort of the behind the scenes work to make a function actually functional and carry out and be able to do its job. All right, and it looks like there's one more output question, but yeah, the output, if you were to try and run this, would just be the list 1, 2, 3, 4, and it would look like list literal notation, right? As I mentioned, we will be going through a sorting algorithm, And when you start to sort, you start to see loops that are nested within one another. But we'll save this for Thursday and call it a day here. Great work on this. References and globals are two seemingly very related, but ultimately distinct ideas from one another that are some of the more difficult abstract concepts to grasp. So as we're practicing these diagrams, hopefully as we get in the habit of drawing them in the particular ways that we do, we can add some clarity to what these concepts are, how they're different from one another, and where you need to be careful. Great work today. We'll have the next exercise is now posted, and the autograder should be available to you already. And we'll have some additional optional practice on these types of diagrams going into next week's quiz posted to the website very soon. Otherwise, we'll see you this coming Thursday in asynchronous content, which will look at sorting and some other cool ramifications of references. Great work.